Good afternoon. Today we arrive to the central lesson of this 1 hour basic introduction to linear algebra. We will talk about a couple of concepts that will culminate with the most important concept, or the most important lesson or feature, I should say, of a vector space, which is the notion of a basis of a vector space. So some of the related concepts that you can see here in the title are the so-called spanning sets and the linear independence. And as you will see later, toward the end of this lesson, the basis is essentially a set of vectors which are both will encapsulates both the concept of a spanning set and of linear independence. The definitions are not, I should say, not hard to understand, even if you see them for the first time. But to really get the point and actually understand the usefulness of these concepts, you just have to go through various examples using vector spaces of different types. The very least vectors in the form of column or row matrices, or vectors in the form of functions, which are more relevant in the context of differential equations. So let me give you a little bit of a motivation. And just to anticipate, the whole idea is that in most of the vector spaces you will encounter, it turns out actually you can describe all those vectors in terms of just a handful of them. How many of them and what types of vectors do you need to have this type of representation is the subject of this lesson. But to an extent, you already know actually that this is the case. So let's look at the R2, right? The vectors in the plane. And you can represent these vectors by many means, right? But let's say for each point in the plane AB, you can represent that point via a vector that emanates from the origin. And you can write that vector in the form of a, let's say, for example, a row matrix or a column matrix. At this point, we don't care one way or another. So let's say you represent each point by a row matrix of two components, A and B. Remember, in the case of vector spaces, you really have only two operations to play around: the scalar multiplication and the vector addition. That's the only way you can actually make more vectors out of several of given vectors. So that's how you can create vectors from other vectors, so to speak, right? By using the scalar multiplication and vector addition. And some of you might have already seen this in another course. As it turns out, actually, any vector in R2 can be written in terms of a linear combination of two vectors, precisely 1, 0, 0, 1. You could make other choices, but these are the most obvious ones, right? So any vector in R2, I can write it in the form of a linear combination of 1, 0 and 0, 1. So you could say that these vectors, let's call them v1 and v2, you can say that to an extent the vectors 1, 0 and v2, 0, 1 really describe, I'm going to put this in the quotation mark because I have to make this a word more precise, they describes the entire vector space R2. And so it is important not only to identify the vectors that will describe the entire vector space, so you can have this efficient representation, but also it's important to actually know, this is 0, 1, how many vectors do you need actually? So for example, do you need only 2? Intuitively, we can say we need only 2 in R2. But how many do you need in other contexts, in other cases? So just to, okay, well, another thing I want to mention right from the onset, because we use this term linear combination, but let's do it more formally. If I gave a couple of vectors, so given a bunch of vectors v1, v2, dot, 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 vn, in the language of linear algebra, a linear combination of them is any expression of the form C1 V1 plus C2 V2 plus dot 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 Cn Vn, where Ci's, these guys are scalars, real numbers in most of the cases, right? So a linear combination, like I said before, is just a way to create vectors out of a bunch of existing vectors. And that's the only way to do it, remember, because these are the only operations allowed or defined in the context of a vector space. All right, so let's then define the concept of a spanning set, because the spanning set is essentially looking at a set of vectors and considering all possible linear combinations, right? So let's write down the definition, and then we're going to illustrate with a bunch of examples. So we call the span of V1, V2, dot 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 Vn the set of all, and again, this is a key word to understand here, all linear combinations with these vectors. So if I take all possible scalars, and I have some problems again with this app for some reasons, hopefully it's not gonna create problems again because I see some missing letters. So the set of all linear combinations with these vectors. This app actually captures a real pen, in fact, on the paper. It's not a screen. So normally it works fine, but all right. So like I said, the keyword is the word all linear combinations, right? So notice that in the previous example, which is kind of obvious, right? So if you take all AB, so if I take all possibles AB in the previous examples and I look at these linear combinations, of course I can generate or describe any vector in R2, right? So you could say then that the span or the spanning set created or generated by the vectors 1, 0 and 0, 1 is the entire space R2. Okay, now in general, the spanning set does not have to be the whole space. It's important in both cases, when it's the whole space and when it's just a subspace. So let's establish another important remark before we move on. A spanning set of any bunch of vectors is a subspace. That means a vector space on its own. In the beginning, the definition of a subspace seems a little bit kind of underwhelming because it's like you don't say much, right? So a subset, which is a vector space on its own, because you obviously take these vectors from a larger space. But it's important to understand that once you have an overarching space, a subset of it, which is not the whole thing, can be a vector space on its own, which can be described by its own basis, right? By its own set of vectors that span that subspace. And so let's actually look at an example already. Let's say the question is, suppose I give you two vectors. So given two vectors in R3, let's say V1, let's use column vectors this time. So V1 equals 2, 0, 3, and V2 equals 2, 2, 0. And then the question is to, let's say, describe the span of these two vectors, V1 and V2. It's kind of a vague question, but sometimes it can be a geometric question if you have R2, R3, and so on, because in R3, obviously you have points, you can represent these vectors by points in the space, in the three-dimensional Cartesian space. All right, so how do you approach the question? Well, you simply look at the typical linear combination. So let's take a typical linear combination involving these vectors. So I have a scalar A plus B times So another scalar b times the vector 2, 2, 0. And again, think about what would this describe if I take all a and b, all possible scalars. Well, obviously it's a scalar product and addition, so this gives me a vector in R3 which depends on two parameters. So let's do the scalar multiplication first. 2a, 0, 3a, 2b, 2b, and 0. 2b and 3a, vector addition. So the spanning set is going to be basically all vectors of this type. That doesn't say much if you don't have maybe an intuitive representation, but that's the answer, right? I mean, span of v1 and v2 in this case is made of all the vectors given by these types of coordinates, where a and b are arbitrary, right? So a and b are arbitrary. And you see, it's not obvious from the beginning whether actually this describes the whole thing or not, right? That's the important question from this point on. Can I describe the whole R3 using this? I mean, we already know this is not the entire space, right? So not the whole R3. The reason it's easy to see that is because if the second entry is 2b, that's going to be always an even number, right? So 2b is even, just as a quick remark. So clearly, if I have a vector, let's say 5, 3, 6, that's not going to be in the span created by these vectors, because the second entry is 3. I mean, it's odd, so it's not going to be described by 2 times b. So it's going to be a subspace, but not the whole space R3. Now, if you want a more or better representations, you could do a little bit more work. You can try to do a geometric representation. So each point in this subspace of coordinates x, y, z will be of the form x equals 2a plus 2b, y equals 2b, z equals 3a. And one could, for example, think of a and b as parameters and then eliminate a and b just to have a geometric description of the subspace in terms of the coordinates x, y, and z. We're not going to do this too often, but just as an idea. You do this, I mean, you'll encounter these type of examples slightly differently framed differently, but essentially the same thing in other courses. So how do I eliminate a and b? Well, basically you solve for a and b from two equations and plug in the other one. Easiest thing is to just just get y by itself, let's say b by itself as y over 2, get a by itself as z over 3, and then plug them into the first equation. So that gives you x equals 2 times a, which is z over 3, plus 2 times b, which is 2 times y over 2. You can cancel the 2, you can multiply by 3 to eliminate the fraction. And those of you who took calculus 3 or excuse me, 2z here, who took calculus 3 might recognize that if I write everything on the left side, or on one side of the equation, 3x minus 3y minus 2z equals 0, you should recognize this as an example of the equation of a plane, right? So a plane is a vector subspace, right? And that's intuitively obvious, right? Because you can think of this plane as R2 in a different orientation, right? I mean, it's just a plane which is neither of the xy or yz or xz planes, right? All right, so let's summarize before we move on to our next page. We have a motivation, right? So the goal is to represent a vector using a handful of vectors, yeah, okay, via linear combinations. We define the concept of a spanning set, which is the totality of linear combinations of a bunch of vector spaces. And then we can address various important questions, like how do we describe the spanning set? Is the vector in a given span or not? And let's actually practice with this a little bit more with other examples on the next page, so stay tuned. All right, so write this title or the subtitle. Is a given vector W in the span of V1, V2, dot, 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 Vn. So given a span of a bunch of vectors, is a given vector W in the same span. Remember, according to the definition, we can reformulate the question in the following way. Can you find a linear combination? Which is to say, can you find a bunch of scalars, C1, C2, Cn, such that W can be written as C1 V1 plus C2 V2 plus dot 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 Cn Vn? That is the question, right? Like in Shakespeare, to be or not to be, that is the question. So this question, again, because to fix the ideas, always leads to actually solving, in the end, a system in C1, C2, Cn, in order to answer the question yes or no. So that means either you actually solve that system, either you can find that linear combination, or you don't, and then the answer is that W is not going to be in the span. Sometimes the answer is easy to spot. So let me give you an example. Let's say I'm looking at V1 equals the vector, just like the previous vectors, 2, 0, 3, and vector V2, 2, 2, 0. Right? And I ask, is, let's say, the vector W equals to the components 2 minus 2, 6 in the span of these two vectors, V1 and V2. Now, sometimes you could guess, like for example, if I look at the relationships, like which scalars, for example, can you find C1, 2Z3 plus C2 such that, so again, take a linear combination of V1 and V2. Can you find C1 and C2 such that this is equal to the given vector, 2 minus 2, 6? Depending on the case, sometimes it's easy to find the scalars. Like for example, if you look carefully, if you multiply the first by 2 and then subtract, you get actually the answer. 2 times 2 minus 2, 2 times 0 minus 2, 2 times 3 minus 0. But it's not always easy to spot the dependence. Sometimes it is, like often, for instance, one of them is the sum of the other, right? So, the W is the sum of the other, so it's obviously in the span. But often, if it's not clear-cut, you just have to go through the solution of a system. So, to find C1 and C2 to see if that system gives you a solution. So in this case, perform the vector operations on the left side and set the components equal to each other. 2C1 plus 2C2 equals 2. 0 times C1, which is just 0. 2C2 equals negative 2. And 3C1 equals 6. Most of the time, if the question is larger or more complicated, one will have to bring the big tools of solving a system via row reduction. Like in this case, the matrix of the system will be 2, 2, 2 on the first row, 0, 2, negative 2, and then C1, which is 3, 0, and 6. And then proceed with reduced row echelon form. In many other cases, though, when the number of equations and unknowns is rather small, you could just bypass that and solve it directly. Like in this case, for example, I can take advantage that the last two equations can be easily solved immediately, right? I get C1 equals 2, C2 equals negative 1, and I can then verify the first equation to see if it's satisfied. If it's not, that means the vector given is not in the span. Now, in this case, obviously, it's verified, so if I plug in 2 for C1 and negative 1 for C2, I get indeed 2. So, yes, W given is in the span of V1 and V2. And one thing to keep in mind, it means that it does not bring anything new to the description of this subspace. So if one will take the spanning set created by V1, V2, and W, it'll be the same as the span of the initial two vectors. Right, so it is useful to think about that let's actually even write it as a remark. If an additional vector, if W is already in the span, then I'm going to put this in quotation mark, it does not bring anything new to the description of that spanning set. So I hope it's clear, because let's say you are in the conquest of describing the entire vector space, right? So then you have a bunch of vectors, you generate a subspace, and you realize it's not the whole thing, right? So if I take the subspace generated by 203,220, we established previously it's a plane, it's not the whole R3. And let's say you want to, bring another vector, so in the hope of describing the whole R3. If this extra vector you bring in, if that guy is already a linear combination of the existing vectors, that means it's still in that spanning set, which you knew already is not going to be the whole R3. So it doesn't bring anything new. You want a vector which is not in the spanning set if you want eventually to describe the entire R3. All right, so let's actually do an example in which let's see, let's ask the same question. Another vector to see if it's in this spanning set or not. So let's say I'm looking at another vector, W equals 101. Is it in the span or not? Well, let's establish, just like before, our system of equations to find C1 and C2. All right, so we're going to do probably another example later similar to this one, because I want to do one later in which I actually need to we're going to do another example in which we actually need to do row reduction. So let's do it like before, just directly. So the three equations are 2c1 plus 2c2 equals 1, 2c2 equals 0, and 3c1 equals 1. So notice from the last two equations, I get c1 equals 1/3, c2 equals 0. But if I plug in these quantities in the first equation, 2 times 1/3 plus 2 times 0 equals 2/3, which is clearly not equal to 1. So that means this system is inconsistent, right? So clearly W is not in the span of those two vectors, v1 and v2. All right, so then for now, if I take the span of all three vectors, the two original vectors, 203, 220, and the new one who I know is not in the span, it's not a linear combination of the other, then how do I describe this new spanning set? It's going to be larger, obviously, right? Because it will describe other vectors which are not in the previous plane. So then, again, the natural questions, obviously I know the answer. It's kind of a trick here because I know already the answer, but a natural question is, and you will know the answer, by the way, don't worry, but a natural question is, will this describe the entire R3, right? So is this everything? Right? How do you actually check this? And as you'll know already, I mean, as you'll kind of get the feeling of it, all of these questions, is a vector in the span? It's not in the span. Does it describe the whole thing or not? All of them actually boil down to, in the end, solving a linear system, or at least analyzing the solution of a linear system. So if I'm asking whether this describes the whole thing, I'm asking this question, I mean, I'm going to put this question slightly differently, right? I mean, in other words, can I find a linear combination of these three vectors such that I can represent any other vector. So the right hand side is arbitrary, unspecified, right? So the question is, can you always find a solution? Is this system consistent for all x, y, and z? Now, fortunately, in some cases, you can answer this question without really solving the system. Here, we have to remember important properties of determinants. If you write this system in the form of a matrix form, so you have the matrix with the columns 2, 0, 3, 2, 2, 0, 1, 0, 1. It happens to be a 3 by 3 system, right? Which means it has a square matrix as a system. And we know that this will have a solution. One of the properties of these systems is that it will have a unique solution if the determinant is not equal to 0. Now, in this case, because it's 3 by 3, it has to be that way, right? Because in order to have a solution consistent, you need to have basically 3 pivots. And then, yeah, so to make sure it describes the whole thing, it can describe the whole x, y, z. And then the determinant in this case is actually not equal to 0, right? If I actually find the determinant 2, 2, 1, 0, 2, 0, 3, 0, 1, I can actually expand it by the middle, by that entry in the middle. So 2 minus 1 to the 2 plus 2 times 2, 1, 3, 1. That's 2 minus 3 minus 2, not equal to 0. So you always have a solution, right? Because the determinant is not equal to 0, this system will have a unique solution. It actually forms a basis. We'll get to that later. You know, the characterization of bases with matrices, basically. But essentially, you prove that you have any vector in R3 described by these 3 vectors. So therefore, the 3 vectors span the entire R3. So let's move on to other examples on the next page. Okay, so let's do another example. And let's say I'm asking this time if these 3 vectors, let's take 3 vectors in R2. 1, 1, 1, negative 1, and let's say V3, 3, 1. Is it the case that these 3 vectors span the whole space R2 this time, right? These are vectors with 2 components, column matrices with 2 components. We're not going to do the full work here, but let's set it up to like before, right? So basically, the question is, can you always find the scalar C1, C2, C3 such that this will be equal to any vector xy? So remember, you solve for the scalar, right? Let's actually, just for the variation, let's actually do it with, or it's a couple of steps with the row reduction. So you put the matrix of the systems, 1, 1, 1 minus 1, and 3, 1, augmented by xy. So basically, the question is whether this is consistent or not, right? Let's not even finish the system, right? The question is it consistent? Can you solve for the variables, for all the variables? And let's do one step in the row reduction process, right? I can subtract the first row from the second. So 0, minus 1, negative 2, 1 minus 3, negative 2, and y minus x. Then I can create a second pivot by dividing the second row by negative 2. So I have 0, 1, 1, y minus x over negative 2, that's like x minus y over 2. It's not necessary to solve to realize that the answer is yes, right? So notice the pivot variables are C1 and C2. I will basically solve in the second equation for C2. It's going to be x minus y over 2 minus C3. Then I can plug it in into the first equation, and I'm gonna get for C1, right? So obviously I'm gonna have basically a solution. It's going to be consistent. Yes, consistent, because I'm gonna have two pivots, and no matter what x, y, and for any C3, I'm gonna get basically a linear combination, right? Not only you get a linear combination no matter what x and y is, you get plenty or infinitely many linear combinations for any vector x, y. So 1, 1, 1 minus 1, 3, 1 will span the entire vector space. You can always solve for C1, C2, C3. In fact, you're going to end up with infinitely many such combinations because C3 is going to be arbitrary. So notice also that, you might notice already that actually 3, 1 is in the span of 1, 1, and 1 minus 1. You can notice that if I take 2 times scalar 2 times 1, 1 plus 1 minus 1, I actually get the vector 3, 1. 2, 1 plus 1, 2 times 1 minus 1. So what I want to emphasize in this example is that it looks like 3 vectors in R2 are maybe more than we need in this context, are more than we need in this example, right? So they will generate the entire thing, but 2 will be enough, right? Because the third one doesn't add anything new, right? It's a linear combination of the other. That's not to say that this always happens, right? So for instance, what if I'm looking at the span given by the vectors, let's say 1, 1, 2, 2. This is kind of a obvious one, right? But let's just do this one. What if I look at the span of 1, 1, 2, 2, minus 1, minus 1? I hope you get the idea what goes on here, right? If I try to describe any vector in R2 via a linear combinations of these, and I take these linear combinations, well, I get C1 plus 2C2 minus C3, C1 plus 2C2 minus C3. No matter what combinations I take, these vectors will have equal components, right? The first component is going to be equal to the second component, no matter how many linear combinations you take. So that means you will never be able to span the entire thing. So this is not going to be spanning the entire R2, right? You're not going to span any other vector with components which are distinct from each other. All right, so again, let's summarize what we did so far. A spanning set is a subspace. You take a bunch of vectors, that's a subspace if you take all possible linear combinations. You can easily check if a vector is already in the span or not. If it is in the span, it's not going to change that spanning set at all, right? And when the question is whether that describes that spanning set the entire vector space, the answer might be yes or no, depending on the relationships of these vectors. So sometimes the answer is yes, but the question is that the most efficient representation? Do you have more than you need in that representation? Or do you still need other vectors so you can describe the entire space. Like in this case, it's no help in the last example that you have 3 vectors, because you still need extra ones to cover the vectors with different components, right? So these 3, now obviously the reason that's the case is because actually, you know, you pick one of them, the other 2 are linear combinations of the first one, right? Because each of them is you can think of it as linear combination of the 1, 1. So actually the vectors 2, 2, minus 1, minus 1 don't bring anything new, because they're just scalar multiples of 1, 1. So you can pick either of them and then drop the other 2. All right, so I think we have enough for linear. Well, let me do another example on the spanning sets, and then we're going to move on to linear independence, and then finally to the concept of a basis. We should do more examples also with involving polynomials, probably. We'll get to that in a moment. So let's do another example with vectors. Let's say again, if I want to check if a vector b, let's say, equal to 5, 7, 9, this is a different notation, is in the span of 1, 2, 3, and 4, 5, 6, let's say. Right? So basically, we're looking to solve the linear combination of these 2 to see if it's equal to 5, 7, 9. And this one, let's do it with row reduction. Again, the answer is probably obvious that the answer is yes, but let's pretend it's not, so we can set it up via the row echelon form. So you look at the matrix of the systems, 1, 2, 3, 4, 5, 6, augmented by 5, 7, 9. We have already the first pivot. We multiply the first row by negative 2 and subtract or add. So minus 1 times minus 2 plus 2. There's going to be minus 8 plus 5, which is negative 3. And then minus 10 plus 7, negative 3. And 0 again. Now we multiply the first row by negative 3. What else? Minus 12 plus 6, that's negative 6. And then minus 15 plus 9, that's also negative 6. Moving on, we can divide the second row by negative 3. And we can also multiply the second row by negative 2 and add, which makes it the entire 0 row. So again, we can stop at this moment. We don't really have to solve it, because as long as the solution exists, then we know the span is there, right? I mean that the vector is in the span, right? The question is whether we find C1 and C2. So clearly this has a solution, because you have 2 pivots each for C1 and C2. If you want to, you can do another step. Maybe let's just do the reduced row echelon form. So we multiply the second row by negative 4 and add to the first. And that gives me 1, 0, 1 on the top, right, on the top row. So that makes C1 equals 1, C2 equals 1. Again, it was probably obvious that 5, 7, 1 was the sum of 1, 2, 3, and 4, 5, 6, those 2 vectors. So yes, B, this vector is in the span of those 2 vectors to begin with. All right, so that's it for the spanning sets. We'll see if maybe I will probably maybe split this lesson into 2. And we're going to do a second part covering the linear independence and basis. All right, so actually, before we call it a day, let's do an example involving polynomials. Same question, because remember, vectors don't have to be matrices only. So let's show that the polynomials, similar question, let's show the polynomials 1 plus x, 1 plus, or x plus x squared, and 1 plus x squared span P2. Remember, that's the notation for polynomials of degree less than or equal to 2, right? That's another vector space. So the strategy is the same, following the definition, and the end product, it's still gonna be basically a system of equations. But let's see how that plays around, and then we're gonna make another summary of how this looks like when you check these things. So remember, again, you're looking for scalar for a linear combination, this time not involving matrices, but polynomial, right? So we're looking at a linear combination of 1 plus x, of x plus x squared, and of 1 plus x squared. And the question is whether this can generate any polynomial, right? A plus bx plus cx squared. By the way, notice that 1x and x squareds are the obvious span. Just as a side note, if you see 1x and x squared as a set of vectors, obviously this will span the entire P2, right? Because clearly any polynomial is going to be a linear combination of 1x and x squared. So this is a question related to other. What if I take a different set of polynomials, right? 1 plus x, x plus x squared, 1 plus x squared. Now, by the way, just so you know, and think about for a second, the answer is obviously yes. Why? Because each x plus 1, x plus x squared, 1 plus x squared is a linear combination of 1x, x squared, which is clearly in the span, right? So that means each of them, well, actually we should check, it depends. Well, the thing is, each of them is actually in that span. So, you know, you can essentially, I mean, 1x and x squared themselves can be written in terms of linear combinations of 1 plus x, x plus x squared, and 1 plus x squared. So these are essentially obtained from the this set that you already know spans P2. But let's pretend that we don't actually notice this. And let's just check by using the definition whether the set of vectors 1 plus x, you know, these polynomials span the entire space P2. Well, essentially, if you do the operations, if you recombine those parentheses, if you expand them and recombine the terms by the powers of x, so if you collect the terms by x, you're going to have C1 plus C3 as the constant term, right, coming from the first and the last. Then the coefficient of x will be C1 plus C2. And the coefficient of x squared is C2 plus C3. So to say that this can generate or represent any other polynomial is to ask whether the system that equates these coefficients, left and right, C1 plus C3 equals A, C1 plus C2 equals B, C2 plus C3 equals C, whether this is consistent, whether you can always solve it for C1 and C1, C2, C3. So it boils down still to a linear system, which if you write it by as a matrix, in the matrix format, that's going to be, if I write it by column, so the coefficients of C1 are 1, 1, 0, of C2 is 0, 1, 1, and of C3, 1, 0, 1. It boils into writing the coefficients by columns of these polynomials. So notice you have 1 plus x plus 0. That's corresponding to 1 plus x if you look at the coefficients by column. The second column are the coefficients of x plus x squared, again starting from the constant term. And obviously the last one are the coefficients of 1 plus x squared written by column. So to say that a set of polynomials span P2 is the same as looking at the span of the vectors formed by their coefficients and asking whether it spans R3. So P2 in some sense is essentially analogous to R3 if you look at the coefficients of those polynomials. The answer is yes in this case. Again, I can look at the determinant. That's the easiest thing to do probably. Let's create some zeros. So let's say I subtract the first row from the second. So I get 1 minus 1, 1 minus 0, 0 minus 1, and expanded by the first column, sorry. And you get 1 minus negative 1, which is 2, and that's not equal to 0, so therefore it has a unique solution, right? So the answer is yes, this set of polynomials will span the entire vector space. So let's summarize the portion of the lesson here on spanning set with the following last remark. To check that W is in the span of a bunch of vectors is equivalent to solving, so to check this, solve the linear system, which in the matrix form is given by the vectors v1, v2, vn by columns, augmented with the given vector that you want to check. So if you look to the previous examples, this is essentially what you did in all of these contexts. You put the vectors by columns, augment it to the vector that you want to check to see if in the span, and see if that system has a solution or not. Polynomials are analogous to this, in which the vectors are formed with the coefficients of each polynomial. So I think that's enough for today. We'll talk about linear independence next time.